everyone, welcome to 10-Minute Physiology. In today's video, I'm going to try to explain to you what long-term potentiation is in under 10 minutes. So let's give it a go. So I'd like to start off with a hypothetical experiment, and in this experiment we have neurons. And these neurons are called CA1 neurons. Now CA1 neurons are neurons that are found inside the hippocampus, which is a region responsible for long-term memory. Now what we're going to be doing is we're going to be attaching these CA1 neurons to voltage sensors. And these voltage sensors are going to be measuring the membrane potential of these neurons throughout the duration of the experiment. Now in this experiment, we are going to be stimulating these CA1 neurons at a specific frequency and measuring the resulting excitatory postsynaptic potential, or in other words, EPSPs, over the course of the experiment. Now this experiment is going to take place over around 30 minutes, so we're going to be collecting data for that amount of time. Now when we complete the experiment, the data that we would retrieve would look something like this. Now it's important to realize that this CA1 neuron is starting off at rest potential, so the resting potential, which is around negative 70 millivolts. And when this neuron starts at negative 70 millivolts, what we see is that the EPSPs sort of fluctuate around a constant value. So the higher the dot is on the y-axis, the stronger the EPSP is. And what you see here is that over the course of the 30-minute experiment, the EPSPs sort of fluctuate around a constant value. And this is a common thing to see when the neurons are at resting potential. So what would happen if we were to depolarize the CA1 neuron from resting potential, which is around negative 70 millivolts, to a more depolarized voltage? Well, let's do this in the second trial of the experiment. So in the second trial of the experiment, we have the exact same setup. We have a CA1 neuron, which is connected to a voltage sensor. This voltage sensor will display the membrane potential of the CA1 neuron throughout the course of the experiment. And we're going to be stimulating this neuron at a specific frequency and measuring the resulting EPSPs. So what we're going to do in trial 2 is start out first with the CA1 at resting potential. So these are the data points that were collected when the CA1 neuron was initially at rest. So we haven't depolarized the CA1 neuron yet. And what we see here is the exact same thing that we saw in trial 1. The EPSPs sort of fluctuate around a constant value. Now what would happen if we depolarize the CA1 neuron? So if we were to depolarize the CA1 neuron, so around this point right here, what we would see with each stimulation is something like this. So we see that once we depolarize the CA1 neuron to maybe a membrane potential of maybe negative 50, negative 40, what we see is that each sequential EPSP increases in amplitude or synaptic strength. And this process that we see here is termed long-term potentiation. So what is happening in this case? So what is causing this long-term potentiation? And just for a side note, long-term potentiation is an increase in synaptic strength that occurs over the course of minutes and maybe even the tens of minutes. So how is long-term potentiation actually working? Let's take a look at the cellular mechanisms. So this right here is the dendrite of the postsynaptic cell. And what we see on the dendrite is that the dendrite will be at a membrane potential of around negative 70 millivolts. So this is going to correspond to trial 1 of the experiment. So what we see on the dendrite of the postsynaptic neuron, or in other words, the CA1 neuron in the experiment, is that we have 2 receptors. The first receptor is the AMPA receptor, and the second one is going to be the NMDA receptor. So remember that the AMPA receptor is a ligand-gated ion channel that binds to glutamate, and it causes a depolarization in most cases. The second receptor is the NMDA receptor, and the NMDA receptor also binds to glutamate. However, it tends to be a little bit slower, and it also tends to allow in a lot more calcium than the AMPA receptor. Now, if you don't know what these receptors are, I have videos in my Synaptic Transmission playlist talking about them in great detail. I highly encourage you go watch those first before you continue on with this video. So now what we're going to do is we're going to bring in our glutamate. Now this is our glutamate molecules, and I have an E in here because the letter E is the one letter code for glutamate. So remember that when glutamate binds to these receptors, it will cause the receptor to open and it will allow current to flow into the cell. And when it flows into the cell, it depolarizes the cell. So we see here that the glutamate bound to the AMPA receptor, allowing current to flow into the cell. Now, what happens when the glutamate binds to the NMDA receptor? So when glutamate binds to the NMDA receptor, what happens is that the NMDA receptor will open. However, no current will flow through it at this membrane potential. And the reason why has to do with the magnesium block. Now, if you watched my NMDA receptor video, you will recall that this receptor can be blocked by magnesium when the membrane potential is really negative. And that's because extracellular magnesium is attracted to the negative interior of the cell, and magnesium will try to go through the NMDA receptor. However, it sort of gets stuck in it like a cork in a bottle. And the reason why magnesium is able to sort of get through the NMDA receptor, but not quite because it gets stuck, is due to the fact that the NMDA receptor is really permeable to calcium. So the reason why we don't see too much long-term potentiation when the cell is at rest is due to the fact that we have this magnesium block. So what would happen if we were to depolarize the cell? So when we depolarize the cell, what we would see is that the magnesium would leave the NMDA receptor and it would allow current to flow through it. Now, the most important aspect of this current is going to be calcium, because calcium is what is responsible for long-term potentiation. So why is calcium important for long-term potentiation? Well, the real answer is we don't know. And it has to do, and people think it has to do with how frequent the stimulation is. So when we stimulate the neuron with a high frequency, what we'll see is that we get a lot of calcium inside the postsynaptic neuron, or otherwise known as the CA1 neuron. And when we get high levels of calcium inside these neurons, what happens is that the high levels of calcium will stimulate the activity of protein kinases. These protein kinases will then phosphorylate proteins that increase synaptic strength, which will therefore lead to long-term potentiation. Now, low-frequency stimulation will cause low amounts of calcium to come into the postsynaptic cell, which will stimulate protein phosphatases, which will cause long-term depression. Now, if these mechanisms don't make too much sense to you, I don't blame you, and this is because we don't know much about how this works. A lot of this is, theoretical, and there's still a lot of research that has to be done with this topic. But the main key points that I want you to take away from this video is that long-term potentiation is a process that basically describes how the excitatory postsynaptic potentials increase in strength over a long time course. And this is a process that requires calcium and therefore NMDA receptors, and this only occurs in specific pathways inside the body. So I hope this helped you understand sort of what long-term potentiation is, and specifically sort of an idea of what types of cellular mechanisms govern it. And I hope to see you in the next video. Thank you for watching, and good luck in your studies.